Good morning. I apologize for not doing the presentation in Spanish, but I will do my best. So I work for this small company in Belgium, and we have this very big client in the energy distribution and production field. And we have lots of interesting problems to work with Python. And 2 years ago, we started to play with microservice and serverless application with Python. The idea of this presentation is to tell about what we faced so far, what the problems we got. Okay, I think it's too small for you to read. I will try to read it for you. So how did we start? We have a concept called engineering tool as a service. This is an internal concept. I'm not sure if it's widespread. But basically, we transform the prototypes developed by engineers in the company into products. It's a mix of software as a service for engineering tools. And so far, it's working well. So when we have a very good idea that works in the lab, we try to build a software product around it. And even if it fails, our engineers, in the end, will have a better tool anyway. So it's almost impossible to fail if we go in this direction. But we got a mission that we had to develop a very important MVP, a minimum viable product, in a very short time frame, 3 or 4 months. And this wasn't the complete picture because we just hired a new team. So this wasn't the complete picture. We had a very short time frame, 3 or 4 months to develop this MVP. We didn't have any web applications working so far. And the company, just in 2017, decided to be a cloud-first company. So everything we designed from 2017 and after that should be designed to run in cloud as a cloud application. So we had all this in the same year, and at the same time, the team was a new hire. So we had a team in Belgium and in Manila in the Philippines with a very long time difference. So depending if we are in the summer or the winter, we have 6 or 7 hours of difference. So it's a little bit tricky to work with this team. The team didn't have experience with Python, so most of them were developers in other languages like C# or Java. At the time, it was very difficult to find good Python programmers in Manila. And I could not say that we have lots of Python programmers in Belgium. It's really hard to hire new people. So we decided to split the MVP in 2 parts. Of course, a Python backend, and a TypeScript single-page application written with Angular. All this from scratch. We didn't use old code to do this. So what did we need to develop? Eng Impact is a branch of the Eng group that works with power production and power distribution problems. So the idea is you need to electrify a region, for example, in Africa or in Asia, and you need to design the best and more economical way possible how to distribute this energy. Where are you going to pass the power lines and so on? So this leads to very nice simulation problems. And the tool that we were building was designed to solve this kind of problem. So the idea is I need this amount of energy, and I have these options to generate electricity. For example, I have to combine solar, wind, natural gas, diesel, and hydrogen power plants, but I don't know how. And the tool will compute the best mix of these different energy sources for your need. It uses lots of complex simulation code. It's a constraint-based tool, so it's not so easy to run, and it requires lots of data. So the application had wizards with 10, 12 pages of data to fill in, to describe your electrical needs, and also how you like to produce and consume this energy, especially because your energy needs change during time. So the tool needs to consider if it's summer, if it's winter, if you need more energy during daylight, or if you need more energy during night. So it's not a piece of cake. The prototype, the internal prototype, was developed using Python 2.7. This was ready. So we had the tool. We didn't build this in 3 or 4 months. It has been developed for the past 2 or 3 years, I think, before we started the web application. So we said, okay, we'll put the existing code in a Docker container, and we'll build the new application around it. We will not touch what is working. Let's just solve the data entry and the cloud part of the problem. That's how we started. Basically, the tool was working with a big Excel file, I think with 20 or 30 sheets that you have to fill in. Lots of repetition of data between the sheets, so it wasn't very funny to work with. But the experts love it to work this way. But of course, if you want to make a product, you would not ask your client to fill Excel sheets. You need to provide an interface and an easy way to input this data. So we decided to go to the web. The simulations had a very different CPU needs. Some of them could run in a few minutes, but the most complex could take about 1 week, and in some cases even 2 weeks to process. So it wasn't it wasn't the typical application that we put on the web. We really need the cloud, especially because sometimes small simulations would require 1 or 2 gigabytes of RAM, but the big ones had to go up to 50 gigabytes. And as we can have multiple simulations running at the same time, it was a really good case for cloud applications, because where would I find other machines with this amount of RAM based on my needs? So the best way for us was to use a pool of computers in the cloud and request the CPU power only when we needed it, because it wasn't needed all the time. We had some challenges here. How could we make this tool accessible to a wider range of users using the cloud? How develop the MVP with the new team? Because they didn't have experience with Python. They started to be trained in Python and JavaScript, so it was really new everything. We have to reuse the existing application that now it's just a container, but we need to scale it in terms of how to make it a cloud application. Even if it's the same application, we had a dynamic need of CPU power. So sometimes the simulation will run in a very small machine, sometimes it needs to run in a very big machine, and our application needs to say, okay, now I need this big machine, now I don't need this big machine, I don't want to pay for it, so you have to destroy or allocate resources based on what you need. We need to minimize the fixed costs, because remember, this was an engineering tool as a service. So the idea is, if I'm not using, I don't want to pay. So we didn't have money in terms of budget to keep a pool of servers, even locally. So we could not buy 15 servers, for example, to run this application locally. So it was a very good case for the cloud, especially because if the product became a success, we would just scale the application in the cloud, problem solved. This is the ideal situation. So we had to create a flexible, reliable, and scalable application, very easy. And it wasn't all. In fact, the research project approved the development of 3 applications at the same time and with the same time frame. So, and the project manager gave a very strong warning to us. He didn't want to pay for any framework building time. So we didn't have time to build libraries and make a very big project around it. And the company is also agile. So all this needs to be fixed in 3 or 4 months. The plan that we started to execute was to adopt microservices. Why? I don't know if the concept of microservices is known for everybody, but the idea is you split the application in little domains, and you try to solve these isolatedly. And you communicate between these little microservices using a known API that you share among these microservices. And this makes the development a little bit easier because the developers of one team are completely free to do whatever they want. So if they want to go Python, they go Python. If they want to go with other programming language, they are also free, but they have to respect the API. So to solve the cost problems, we said, okay, now that we choose microservices, why not go serverless? We didn't have enough problems at the time, so we decided to do microservices, and they should also be serverless. The idea of serverless or functions as a service is that instead of having a server waiting for requests in the cloud, you simply create a configuration telling, okay, if you receive a request, instantiate this function, and this will do the processing for you. At the end, the cloud provider is free to destroy the instance, and you only pay for the time it was running. So in terms of cost, it's very interesting because you pay less than 1,000 of euro cents for one execution. And if your application is not used every time during the day, for example, if it has a peak of utilization around noon or in the end of the day, these are very special cases where serverless are good. And they also solved the problem we were afraid to have regarding scaling. So what if we started to have 50, 100 users, and they all try to use the application at the same time? We didn't want to do the scaling of the services ourselves. And if you go serverless, most cloud providers will scale it for you. So for example, if you receive 100 requests, instead of queuing the requests, you can have 100 instances or 50 instances. This is managed by the cloud provider for you. So this was very interesting in terms of infrastructure. We also built the front end as a set of components. So for example, screens and common controls could be shared between these three applications. And the idea was to have maximum reuse. Microservices, because with three applications, we detected that at least 25 or 50% of this application was kind of boilerplate code. You need to do user management. You need to figure a way, for example, to manage notifications to your end users between the front end and the back end. You also need, for example, to manage the computation requests that you are going to make, that we call it the computing kernel. This is the piece of code that manages the cloud provider to create instances and request the computation and also destroys it. So we said all these three applications will share this common functionality. So let's build them as microservices. This is the API. Each team took one microservice. In the end, we put it all together, and we still have time to implement the application itself later on. Each application would become a new microservice. So we had about 6 or 7 microservices to solve these problems. The idea was really to focus in the dependency of the team, because as you know, it was an agile. It's an agile company. We didn't have architecture or something to force people to use specific tools and so on. We need to decide ourselves how we're going to build this and self-organize. In the end, we were a team of 10 developers, partly in Brussels. So I think we had 4 people in Brussels and 6 in Manila. This changed a little bit over time. We decided to apply some rules for the building of the microservice. So for example, the microservices have completely independent databases. So no shared table, no direct access to their data. This is a concept from the Microsoft world that we really enforced. So when one team asked, okay, how do you implement this in the database? We said, no, you don't need to know. Your knowledge ends in the API, If the API is not fulfilling your request, okay, let's change the API. But you don't touch my database, you don't touch my tables. Okay, this is very important. All communications at the API level, no imports between microservices. And this was really tricky because we also use a single repository for everything. So as a Python programmer, you see the module you want, 2 folders before yours, and you try to import and you say, no, there is no imports between them. We don't use this. This is the main idea, so they could be rewritten independently in case of failure. For example, if one of the teams didn't manage to do what we expect, we would simply move on. I will do a little bit faster because I'm running out of time. So serverless, low cost, on demand, no server upkeep, so nobody to watch the server running, independent design of each endpoint, scalable, no downtime when deploying, the perfect solution. The department also embraced DevOps, so every developer is able to deploy. We don't have a central administrator for everything. We split development in 4 stages, called development, QA, staging, and production, the classical solution. We worked before with Flask applications, so before adopting microservices, we had some applications in the department using Flask, because most of the time they just want to provide an API for data scientists and engineers to call. So we build everything on top of it. We try to use Zappa. Zappa is a Python framework that encapsulates UISG applications to run with Amazon Lambdas, for example. It also supports other cloud providers. But we didn't think that it would be a best match because we said if we are going to the cloud, we need to design for the cloud. If we just adapt, it will not go very well. If we had a Django or a Flask application before, and the goal was, okay, now we will make this serverless, then Zappa would be a good solution, but it wasn't for us. And we also played with AWS Calis. It's a framework developed by Amazon where it's heavily inspired in Flask. So if you know how to program in Flask, you are almost ready to use Calis. It's really a few lines of code that change. It's very nice for a first contact with the serverless world because you can write a kind of Flask application, and Calis will create the lambdas, upload the lambdas, do everything in the cloud for you with a single command. So it's a really impressive tool. So we decided to go serverless. This is a little bit tricky because they use the same word, but serverless is the name of a JavaScript framework that is used to deploy code to the cloud. So for example, you create a YAML file telling I have these functions use these pieces of code, and using the serverless framework, it will create a zip file and do everything it needs to upload this to the cloud. So it's a kind of framework to deploy your code to the cloud. It's very good. It's multi-language, so you can deploy Python functions. You can develop. You can even use other languages like Go, Ruby, and really many languages. It's also integrated with many Amazon services, like the queuing service, the object storage service. So it's really handy. We went Python 3.6. Even if the original application was Python 2.7, we said, okay, Python 2.7 is dying. This was 2017. We said we will not create more code to migrate in the coming years. So we went to Python 3.6. We heavily adopted type hints. This is a positive experience because this really improves how we coded. Type hints are code annotations that you add to your function. So you say, this parameter, I expect an int. That parameter, I expect a float. And this function should return a string. And when you run a static analysis tools or a linter, for example, it will say, okay, this function is expected to return a string, but it's returning none. So you have a warning in the command line, and it's much easier to debug than waiting for the error to happen. So this really improved the communication in the code reuse, especially because we have people developing code and using code developed by other guys, and we had no time to discuss. Remember that we had 6-7 hours difference, so we just have 3 or 4 hours in common to work each day. We also organized the code in a different way, so instead of having a kind of function that receives the web request and route it into our code, each endpoint is a separate Python module. And then we have every endpoint in a separate folder. And we have a common code, it's the shared code subfolder, that contains the libraries and the data models that they share. This is the infrastructure of a single microservice, and as I said, the microservices do not communicate using Python, just the API. We also built a DIN layer to access the other microservices, because, for example, if microservice A wants to call microservice B, we need to have some code to prepare the web requests, to add the authentication headers, to check the parameters, and so on. So this, we built kinds of small Python libraries, so each microservice could access the other. For all developers, it was just Python. The web part was a kind of abstraction. And this also worked very well. There is a very important thing here. The DIN layer wasn't written by a single developer. The DIN layer was written based on the API specification. So when something went wrong here, it was a good hint that the documentation wasn't good enough. Because if the documentation of the API is not good enough to write code that uses the API, it doesn't smell good. So we used this to reinforce the importance of the API and the documentation in the project. So we didn't use any web framework, we didn't use Flask, we didn't use Django, we just used plain Python code to implement all this. The functions are very simple, around 10 or 15 lines of code for each endpoint, because they have very few responsibilities. Extract parameters, enforce security rules, call the service of the endpoint, and then generate the error code. So each endpoint is very small, you can read it in a single screen. I think we have just 2 or 3 endpoints that are this size. Most of them are really small. Easy to test, easy to change. And we also had to develop common libraries for logging, to communicate with Sentry. It's also a very good tool. If you never use a Sentry, have a look on it. And we are heavily dependent on a pipeline, because as I said, we were 10 people working in 2 different time zones in at least 4 offices around the world. So we didn't have a lot of time to talk and discuss. We really need to code. So we built this pipeline to stop coding wars. Coding wars happens when, for example, you commit your code and in the morning somebody added blank lines in between them, or they changed the styling of the stuff. So to stop this kind of stuff, we said, okay, let's agree to a common coding style, let it be enforced by the pipeline. So when you commit, the pipeline will normalize your code using, this is yet another Python code formatter. It's a tool developed by Google. So we customized the style, we agreed, and that's what we use. The code to be accepted needs to pass into Flake 8 tests and in the MyPy. MyPy was very, very important because using the type hints that I talked before, it was able to enforce certain parameters for code quality during on every commit. So we didn't even have to wait to have a bug later on. Tests, and especially a commitment to have 70% of test coverage. This test coverage was enforced on each commit. So if you added your code, all tests were passing, but the test coverage went below this per microservice, you get a red light in the pipeline. So it wasn't good. We tried to maximize automation, so we didn't go to manual code reviews and code reviews meeting because we didn't have time for this. we said, okay, if your code is good enough to pass by all this, we don't need to do a code review every week or every month. What we did was a kind of random samples of the code, especially when the pipeline went red, or if we detected a bug, then we said, okay, let's have a look on the code that generated this. And whenever we found something strange, we called the developers and said, hey guys, this is not the way to solve this problem, let's try it that way. And then we also agreed and started coding in a different way. So red pipeline committers are punished in Slack, so we blame with jokes, on Slack if you burn the pipeline. And we did this random code quality checks. API design was also key to our process because we need to design the API first, document the API, be sure that everything was okay, so other teams could use the same API. I will pass this fast because I'm really running out of time. The Python stack we used was a very plain one, simply Boto3 for the AWS service requests, the request library itself, and DynamoDB to do the interface between the data model and DynamoDB. Documentation was key to our success, so everything is on Git. We had a special folder for documentation. We used Sphinx to extract the doc strings and build the documentation. We also used Markdown and REST pages where extended documentation was needed, but everything was available on Git. Everybody could build the documentation on their own machine. For the API documentation, we used RAML and then converted to Swagger. RAML is a format where you can specify the API. Now it's called, the Swagger now is called the Open API. Also generated with a single command, available on Git, and everything is stored in the same repository. It also makes it easy to keep the documentation in a good way, because developers cannot say that they didn't see the documentation, it was there. Challenges for Python, not the fastest language, uses a lot of memory. If you are really measuring how much memory you are running and you need to do this for cloud applications, it can be a problem. The startup time of Python is still slow, but it's improving, so you have to design your application considering all these. Dependencies, when you have to create a zip file to deploy your function, you get a good idea about how many modules you are using, because sometimes you are installing 2 or 3, but each of them will call other 4 or 5, and in the end you have to deploy 20, 25 packages for isolated installation, so you have to really consider this. Endpoints on Amazon have something like 30 seconds to reply, otherwise they are shut down. So you have a time limit to do your job. So this is how it's built. We won't have time to talk about that. Python solutions that we used, we minimized the imports. We really worked with lazy initializations, because if you don't pay attention and if you initialize everything in the main Python module, for example, you forget that this is executable code. So even if you are not using that, the initialization was run at the time you made the import. So you have to keep this in mind, otherwise your startup time goes up very, very easily. We need to optimize from time to time, so maybe in the future we are going to play with Nuitica, the Python compiler. And also we'll try to write some resource critical code in other language. So far it's not needed. So we split the application in the user microservice, the billing microservice for metric collections and also resource consumption. Billing is very important because this is the guy that says you are running out of quota, for example, you run out of space. Notification for WebSocket management, and the computing kernel, that this is the little monster that controls the cluster on Amazon. We used all these services in AWS. It's lots of acronyms. And in the end, we had something like this. I don't think it's very clear. But basically, this is to solve the security and authentication of the web application. And then on each square, you have the infrastructure for each microservice with a set of lambdas. Sometimes you have a queue. They all have the independent database, and they talk with each other using a common API. Okay? So the computer kernel, the user microservice. This is the application. This is an internal application. We are not allowed to say their name, so there is a mark here. But this is the application that uses the other microservices and builds a single web application to the client. So this is how it looked in the end. So this is the data entry form. This is the JavaScript application. Here we have the WebSocket notification. So if you have something running for 1 week, you will not wait until it finishes. So when the user is using the application, it can receive notifications from the backend telling, hey, that code, that simulation just finished, and you don't need to refresh the page and so on. So we use WebSockets for this, and the front-end guys built a nice engineering application. This is the Lambda execution time overview. So this is the average runtime. It's too small to read, but the topmost here is around 13 seconds. You say, yeah, 13 seconds is not the end of the world, but remember that we have 30 seconds to reply, so it's almost 50% of the maximum time. It's become a dangerous situation. And what does it take? Why? What part of the application is taking 13 seconds to complete? Excel manipulation. Do you remember that the tool was using Excel as input file? So we have to collect all this data and create an Excel file to be the input. And Excel manipulation is extremely slow. Okay, so 13 seconds can be a lot when you have this kind of situation. So I think here it's clear. You have the Excel to start the simulation. So we have here they are around 13 seconds, 11 seconds. So you have some metrics here. I will share the application. And these are the fastest as well. So when you just have an access to the database, get a counter, list users, and so on, the code will run in 33 milliseconds, 36 milliseconds. Good. Okay. Always measure this stuff. So the future steps for us is optimize the runtime, experiment with async. I really love Python async. I wrote lots of articles about it. And we want to use it, for example, we can clearly split in each endpoint the part that enforces the security and gets the data in 2 levels. So for example, you can get the user credentials and check the parameters necessary to execute the operation using async. And then the code will execute almost in the same time, because when you are working with microservices, you have lots of I/O time. So whenever you have I/O, async is a very good case, has a very good case to be applied. We want to try with other languages. We didn't decide which languages yet, because so far we have been using Python, and I think everybody's happy. Maybe add some GraphQL endpoints in the future, because the engineering scenario is very, very big, so we have sometimes around 400 kilobytes being written in a single call. It starts to be too big, so we want to specialize this using GraphQL, and then we'll get some bits of it when we need. And also work with AWS Step Functions. This is a kind of state machine that coordinates Lambda functions on Amazon. And that's it. So our MVP was delivered, I think, in May. The initial date was February. So we weren't really late. We could have delivered it in February, but we got extra months due to a business situation that changed. So it was delivered in May. It was running. The day I came here, I think on Thursday, we made another release. Everything's still working. So for us, Python is still a strong contender in software as a service and functional as a service fields. with discipline and tools, we can really work with these drawbacks. Serverless is not free. You have to spend a lot of time designing and taking care of your code. So when you see, okay, all my problems are gone, the infrastructure is not a problem. But no, you have to think that you pay a huge price, and it really impacts the application design and testing. The cloud is not free. If you make a mistake, I had one engineer that made a mistake, a function calling another function, and I think easily we got to 20 million calls, and you pay for each of them. So they are not very expensive, but if you do this 1 million times, it gets expensive. So you need to keep an eye on it. Now we have a new set of tools, and we are able to bootstrap new applications because these microservices are reusable. We can continue to develop them independent of the original application. And last Monday, we started the 4th application that we use this framework. Okay, so this is the team that helped to develop this. This picture was taken in when we visited Manila. And we have the project owner looking what we were doing here. Here's the first one from the left. And that's it. So if you have any questions, Engine Impact is also hiring Python engineers in Brussels and in the Philippines. Okay, so if you want to work in any of these places, this is the website. There is a small link there where you can submit your CV. And that's it. Thank you very much.